So, we are studying this converter where on the AC side I have a balanced 3-phase voltage. This is connected in Y. The voltage source is a 3-phase voltage source connected in Y. So, the converter has 3 legs. In each leg there are 2 thyristor valves. The DC side is represented by a constant current source ID. The voltage across the DC side terminals is VD. So, the voltages on the AC side are EA, EB and EC. So, we assume expressions for EA, EB, EC as root 2 by 3 V sin omega OT plus 150 degrees. EB is root 2 by 3 V sin omega OT plus 30 degrees, and EC is root 2 by 3 V sin omega OT minus 90 degrees. So, the valves are named as 1, 3, 5 as far as the upper commutation group is concerned, and the lower commutation group the valves are numbered as 4, 6, 2. So, we actually formed a table where it was shown that each cycle can be divided into 6 equal intervals, and in each interval which are the thyristor valves that conduct, and what is the voltage across the these side terminals, and what is the voltage across one of the valves, say valve 1. Okay. So, what we will do is we will try to see what happens on the AC side. So, there are 3 currents on the AC side. Let me call this instantaneous current as IA, IB and IC. So, as I have said, the current on the DC side is ideal, it is constant, whereas the voltages on the AC side are ideal, which are sinusoidal and balanced. So, there is a deviation from the desired value for the voltage on the DC side, and we will see that even the currents on the AC side deviate from what is desirable. So, they are actually not sinusoidal balanced currents. So, let us look at one of the currents, say IB. Suppose I want to plot IB as a function of omega OT. So, suppose I plot IB. Now, when will IB be non-zero? See, look at this circuit. IB is non-zero when thyristor valve 3 conducts or thyristor valve 6 conducts. Okay. So, if there can be a duration where neither 3 nor 6 conducts, so then IB is 0. Now, what happens when 3 conducts? What is the value of IB? IB is same as ID. See, this ID has to flow somewhere. So, at any instant ID will flow through one of the 3 valves 1, 3, 5 and one of the 3 valves 2, 4, 6. Okay. So, the circuit has to be completed. So, the circuit is completed by one of the valves in the upper commutation group, one of the valves in the lower commutation group, and two of the three phase voltages. Okay. So, if 3 conducts, then the current IB is equal to ID. If 6 conducts, what is IB? Minus ID. Okay. So, let us try to draw the waveform of IB. So, if I take the instant at which 3 is turned on, so what is the instant at which 3 is turned on? What is the instant? We are given some, we are given a name for that. What is the instant or angle? No, I am not asking. We are actually considering a more general operation where it is not diode operation. Alpha. So, at alpha, thyristor valve 3 is turned on. So, if thyristor valve 3 is turned on, then alpha, at alpha, IB is equal to ID. So, it is equal to ID. So, this is equal to ID. So, for how long this will remain at ID? Up to, as long as 3 is conducting. So, up to what instant 3? Alpha plus 120. So, suppose this is alpha plus 120. So, up to alpha plus 120 degrees, thyristor valve 3 is conducting. Okay. So, this is the duration for which valve 3 conducts. So, at alpha plus 120, what happens to IB? See, at alpha plus 60 degrees, one thyristor valve is turned on, that is, say suppose this is alpha plus 60 degrees, 4 is turned on, thyristor valve 4 is turned on. At alpha plus 120, 5 is turned on. Okay. Now, when 5 is turned on, let us go back to the circuit. When 5 is turned on, then 3 is actually off, 3 is off. So, if 3 is off, 5 is turned on. So, IB will be non-zero only if 6 is conducting, but is there a possibility of 6 conducting when 5 is turned on?
There is, but since 4 is also conducting, it cannot.
No, there is no possibility. See,
There is a possibility.
Why?
Alpha plus 180.
no, at the instant of turning on of 5, is there a possibility of 6 conducting? No, it is actually the thyristor valve which is conducting, 4 which is conducting. Okay. So, since 6 is not conducting, IB is 0. Say, IB will be non-zero only if and only if 3 is conducting or 6 is conducting. So, if neither 6 conducts nor 3 conducts, then IB is 0. So, if I want to plot the waveform of IB from alpha plus 120 for say duration of 60 degrees. Okay. So, suppose this is alpha plus 180 degrees. So, up to alpha plus 180 degrees, ID is 0, IB is 0, IB is 0. So, at alpha plus 180 degrees, which thyristor valve is turned on? 6. So, when 6 is turned on, then IB is non-zero and it is equal to minus ID. So, I have a duration of 120 degrees for which valve 6 conducts. So, when valve 6 conducts, IB is minus ID. Now, this continues up to what instant? So, I can show one more instant here, alpha plus 240 degrees, alpha plus 300 degrees. So, at alpha plus 300 degrees, which thyristor valve is turned on? Sorry, 1 or 2? 2. So, when 2 is turned on, so go back to the circuit. When 2 is turned on, obviously 6 is not conducting. So, when 2 is turned on, is there a possibility of 3 conducting? When 2 is turned on, there is one more thyristor valve which is conducting. Which one is that? At any instant, 2 thyristor valves are conducting. One from the upper commutation group, one from the lower commutation group. So, when 2 is turned on, 1 is conducting. So, 1 and 2 are conducting means neither 6 nor 3 is conducting. So, IB is 0. So, IB is 0. So, IB will remain 0 for a duration of 60 degrees, that is up to alpha plus 360. Alpha plus 360. So, then the cycle repeats. Okay. So, again it goes to plus ID, so on. So, even before alpha, that is for omega OT slightly less than alpha, ID will be ID is 0. Sorry, IB is 0. Sorry, IB is 0. Okay. So, this is the waveform of IB. Now, what I intend to do here is to get the expressions for harmonic component. So, it is not equal to the desired waveform. The desired waveform is sinusoidal. So, we see that there are harmonics, but one can easily say what is the RMS value. So, what is the RMS value? RMS value of AC side current. See, though I have drawn only one phase current IB, IA and IC are identical to IB except for a phase shift of 120 degrees. Okay. So, IA will be identical to IB except that it leads IB by 120, IC is identical to IB, but it lags IB by 120 degrees. So, if I take RMS value of AC side current, so IB is an AC side current. So, let me use the notation I for RMS value of AC side current. So, can we try to give an expression for this without any computation? Root 2 by 3 ID. Okay. So, it is having a magnitude of ID for 2/3 of a period. Okay. So, the RMS value will be square root of 2 by 3 into ID. Then let us look at the expression for fundamental component and the harmonic components. So, if I take the RMS value of the fundamental component of AC side current, so I will call this I with a subscript 1. So, I will leave it to you to get an expression for this. So, I will give the answer. It is root 6 by pi into ID. So, I get an expression in terms of ID, in terms of the DC side current. Okay. So, it is just application of Fourier series. Now, one has to note that this particular waveform has a particular, has a symmetry. What is the symmetry? What symmetry? It has quarter wave symmetry. We can't say anything beyond that. See, odd or even is very difficult without knowing the value of alpha. Okay. So, it has quarter wave symmetry. So, one has to integrate only for 90 degrees, but since there are durations for which the waveform is 0, you do not even need to integrate for 90 degrees, you have to integrate for what is the duration?
Alpha to alpha by
60 degrees. 60 degrees. Okay. So, that is the RMS value of fundamental component. If I want the RMS value of Hth order harmonic component, of the AC side waveform, AC side current. So, when I use the word harmonic component, I mean H greater than or equal to 1. H equal to 1 means fundamental. Okay. So, of course, we use the subscript 0 for average value, but when it comes to the quantities on the AC side, average is 0. So, we are talking about AC side current, so the average value is 0. So, IH is the harmonic RMS value of H third order harmonic component. Of course, for some values of H it is 0. For what values of H it is non-zero? Odd values. Okay. For odd values. So, that means by definition of harmonic, H is greater than 1, that means 3, 5, 7. H equal to 1 means fundamental. So, when I say harmonic, I mean H equal to 3, 5. But what happens to the value of IH when H is equal to 3?
Again it will be 0.
Why?
Because the 3 are balanced.
Yeah.
IA
plus IB plus IC is 0. So, when the 3 currents on the AC side, IA plus IB plus IC is 0, we saw in the last class that the third harmonic, not only third harmonic, all the triplen harmonics are 0. So, that means even harmonics are already not there. So, the triplen harmonics are also 0, that means third harmonic is 0, 9th harmonic is 0, 15th harmonic is 0, 21st harmonic is 0 and so on. So, what remains are the harmonics of particular order, it can be given by an expression. So, what is the first harmonic component that is present? 5. So, I will leave it to you to show that this IH can be written as, it can be written in terms of ID, it can be shown to be I1 by H, whereas see we have already shown that I1 can be written in terms of ID. So, the harmonic component can be written as I1 by H. So, it is 1 by H into the fundamental. So, this is the case if H is equal to 5, then
6k plus minus 1.
so it can be written as 6k plus minus 1, where k is taking all positive integer values. So, if you take k is equal to 1, you get 2 values 5 and 7, k is equal to 2, you get 2 values 11, 13, k is equal to 3, 17, 19, so on. Okay. So, these are the harmonics that are present in the AC side current, and if it is equal to 0 otherwise. Of course, yeah, one point to note is harmonic component. By harmonic component, I mean H greater than 1. Okay. So, one should not get an impression that I1 is 0, because I am talking about only harmonic components. I have said otherwise it is 0, I mean it may give a wrong impression that I1 is also 0. I1 is not 0, I1 is given by root 6 by pi ID. So, I am asking you to derive this expression for I1, IH, and if at all by chance if it is not clear to you that the RMS value I is equal to root 2 by 3 ID, then you have to do that also. Okay. So, see this is something which is familiar expression if which can be written straight away without any integration, that is root 2 by 3 ID is equal to RMS value. But if it is not familiar, no, I mean it is okay, you can still apply the definition of RMS, root of the mean of the square. Okay. Now, what we have seen so far is the analysis of this, and we got the expressions for the DC side average value and the harmonic components on the of the voltage on the DC side, and on the AC side the currents are not sinusoidal. So, we got the expression for RMS value, fundamental RMS as well as the harmonic RMS.